G'day chemistry students. In this video we're going to be covering dot point 4.3.4. We're looking at spontaneous reactions and Gibbs free energy. Let's get into it. First off, I'd like to talk about our new thermodynamic measurement for this video, Gibbs free energy. We usually show it quantitatively in equations as G, but more commonly, just like all of our other measurements that we've talked about so far, we're better off talking about the changes in Gibbs free energy. These are things that are a lot more easier to calculate, and that's shown as delta G. Gibbs free energy is usually measured in joules. And to define Gibbs free energy, sort of in the opposite light to what we were talking about with our entropy, Gibbs free energy is probably best defined as a measure of useful energy, or the energy which is able to do work. Now, like I alluded to in the previous video, useful work in chemical reactions can be really tricky to define and talk about in simple terms. But generally, useful energy might be the energy required for, say, chemical reaction or forming bonds or breaking bonds or anything like that. But as well, another good example of useful energy may be the energy that is used to produce electrical energy in some specific circumstances. In particular, I'd be thinking about the energy required to produce electricity in, say, a galvanic cell when I talk about this. Now, generally, we can relate Gibbs free energy, enthalpy, and entropy changes using the equation that I've got below here. And we'll start to use this sort of a little bit in the next lesson, but then in future lessons when we start doing calculations as well. And that's that delta G, or the change in Gibbs free energy, is equal to the change in enthalpy minus T, or temperature, times the entropy of the system. So in other words, what we're kind of saying is, well, the useful energy that we have is equal to the total energy that we have minus our useless energy value there, T times delta S. So if I was to rearrange the equation and sort of make delta H the subject, another way of putting this is that the total energy that the system has is the useful energy plus our T delta S term, which refers to the wasted or the useless energy. Keep in mind that all of the definitions that I've been using so far are quite loose definitions, but for the scope of this course, they will definitely suffice. We're a little bit less worried about what all of these different energies mean, but what we care about more is how we go about using them. And the most important thing for this equation here is that delta G is in some way a measurement that is determined by the entropy and enthalpy of the system, and we're going to learn how to use delta G in the following video. But for now, I want to talk about more just generally the concept of spontaneity, something that we looked at in module 3. When we first looked at it, I said that they were chemical reactions that could proceed freely under specific conditions, that some reactions like this precipitation reaction here would just go ahead under standard conditions, but other reactions, like the decomposition of water, required some sort of input to enable the reaction to proceed. It just didn't freely do it itself. So I'm going to sort of change our definition now that we've been talking about spontaneity sort of over the course of module 3 and into module 4, and redefine it now as chemical reactions are considered to be spontaneous when they can occur freely without continuous external energy input. So for example, with our decomposition of water, this reaction can only happen with a constant steady supply of electrical energy, thus making it non-spontaneous. We can actually use Gibbs free energy to determine whether or not a process will be spontaneous. You may see these terms getting thrown around a little bit. They're certainly less used than exothermic or endothermic to describe reactions. But if we're looking at delta G and trying to determine whether or not delta G is more or less than 0, we can define them as endogonic and exogonic in exactly the same way that we've defined exothermic and endothermic reactions for enthalpy changes. And you'll notice as well that these Gibbs free energy diagrams look very similar to the other energy flow diagrams that I've shown you when we were looking at previous energy concepts. But these ones in particular are focusing on the change in Gibbs free energy, or the change in the useful energy that the system of chemicals have. And what we'll see is that for an endogonic reaction, probably most comparable to endothermic reactions that you've seen before, but not exclusively endothermic reactions, but any reaction that's endergonic will end up increasing in energy by the end of the reaction. And what that means is that the reaction is non-spontaneous. It means that energy has been absorbed through the reaction process, and overall, Gibbs free energy has increased as a result. Conversely, when we look at exergonic reactions, we see that the reactants have decreased in energy as they hit their products. And what that means is some energy has been released in some way, shape, or form, meaning that delta G is less than zero. There has been a loss of energy from the system, and that is going to mean that the process was spontaneous. Keep in mind that these energy changes that are being shown here are not heat exclusive. There may be a gain or a loss in heat that can be measured sort of more in line with what we were looking at in our enthalpy calculations and experiments, but these energy changes could be through electrical energy, light energy as well. And so this is what we see. Either reactions that absorb energy or reactions that release energy. And that absorbing or releasing of energy, as I said before, could be through heat, but it could also be through other means such as electrical energy or light, as shown in the couple of examples of reactions that we have looked at before in class. Thank you very much, everyone. In the next video, we're going to be looking at how to do Gibbs free energy calculations as a way to be able to predict the spontaneity of reactions, whether or not they will spontaneously occur under those standard conditions. But until then, have a good one.